Welcome to Counting with Python's Counter. My name is Christopher, and I will be your guide. This course is all about Python's counter class in the collections library. You'll learn about counting problems in computing, how to use the counter class to write less code, practical algorithms where the counter class is helpful, and multisets. Sample code in this course was tested with Python 3.10. The counter class is mostly unchanged. I do use f strings in a couple of places, but besides that, the information is fairly version agnostic. A common problem in computing is determining the frequency of items in a sequence. Or, to put it more simply, counting things or groups of things. If you're counting one thing, you use a variable. But if you're trying to count a whole bunch of things or track multiple things, then Python's counter class can help you do that. The first lesson will be on counting problems. In the previous lesson, I gave an overview of the course. In this lesson, I'll introduce you to solving counting problems without Python's counter class. Doing it the hard way first. My mother would be proud. Computing is full of counting problems. One of the first things you learn to do with a sequence, such as a list, is to find its length. That's a basic counting problem. How many things are there in that sequence? Finding the length of a sequence is only the beginning, though. What about grouping things together in your data? Counting these kinds of things is called determining the frequency of an occurrence. Let's go to the REPL, and I'll show you what I'm talking about. Let me start without using any libraries, just some straight Python data types. Take the word Mississippi. What if you wanted to count the occurrences of each of the letters in the word? You could create a dictionary. Then for each letter in the word, check if that letter is already in your dictionary. If it isn't, then create and initialize the key value pair to 0. And then either way, increment the counting value. Looking at the result in the dictionary, you'll see a key for each unique letter and the corresponding count of the letter as the value. 1 M, 4 I's, 4 S's, and 2 P's. By the time you're done, you're going to be tired of Mississippi, I promise. Initializing a new key in the dictionary can be done in other ways. Let's skin the proverbial cat. What a horrid expression. Same initial dict. Same for loop. And this time, instead of a conditional to initialize the value and a line increment, it can be done in a single statement. The get method of a dictionary takes a default value parameter. So in this case, either the letter is fetched and then incremented, or 0 is returned and incremented. The new value is set into the dictionary at the corresponding key. The counterdict now has the same result as before. And you could also do it with the default dict class. Default dict is a specialty dictionary class that lives in the collections module. And this time, instead of creating an empty dict, you create a new default dict class passing in int. The hint here is in the class's name. It is a dictionary with a default value. Passing in int means that if a key isn't found, create it, setting it to an integer. The default value for an integer is 0, so our new key will be set to 0. As before, same loop. And this time, a much easier to read line. This is doing the same thing as get before, but by using the default dict, the default's key behavior sets it to 0, and then you can increment it. Looking at the counter, you see that it looks a little different, as the result isn't a plain old dictionary, but a default one. The counts inside are the same, and as default dict inherits from dict, anything you can do with the base class, you can do with this fancier one. Okay, I think you've got a taste for the problem. As this course is titled Counting with Python's Counter, it shouldn't be a surprise that the next lesson is on using the counter class. In the previous lesson, I showed you a counting problem and tooled a solution by hand. In this lesson, I'll show you how to use Python's counter class to make this simpler. The counter class is a member of the collections library, and like several of the other classes within that library, it is based on a dictionary. In this case, the keys are the instances of things being counted, while the corresponding values are the count of those things. You came here to code. Let's dive into the REPL. Think back to the Mississippi letter counting problem in the previous lesson. Here is a much shorter version. Yep, that's it. Creating a counter object results in counting whatever iterable is passed in. A string in an iterable context gives each letter inside of the string, so passing a string to counter counts each of the unique letters. Counters can also take lists. Passing in the list in this case, the list is turning the string into the iterable of letters, and passing the list into counter ends up in the same result. You can also pass in dictionaries. In this case, the key value pairs indicate objects being counted and their corresponding counts. Essentially, the data structure our results got stored in back when a variety of cats were in danger. All right, I'll stop with the cat jokes, I promise. You can also pass in named arguments to counter. Each named argument is treated as a string with the corresponding value being the count. Alternatively, you can give it a set. Remember that sets are also constructed based on iteration, but they can only hold one instance of each thing in the iteration. Creating a set for Mississippi iterates on the letters, keeping only the unique values. Create a counter based on the set results in a count of 1 for each of the letters. Counters are just dictionaries. You can use any hashable item as a key and store any value. The only caveat is that if the value is not an integer, you won't be able to increment that count later. So, although it won't stop you from storing anything, if you want to take advantage of some of the key additional features of counter, you really only want to store integers. Let me show you another example using arguments. Here, I'm storing integers, and one of them is negative. What does minus 15 tomatoes mean? Well, maybe you owe your neighbor that many, and this counter is tracking what's in your fridge. You know how a second ago I mentioned you can increment the counter later? Well, it's later. Little deja vu. And one Mississippi. And now with the counter instance, I can change values by calling the update method. Like the initializer, update takes any iterable. Iterating on Ohio adds two O's, an H, and an I to the count. You can see the difference here. You can also call update with a dictionary. That's a lot of I's. Notice updating with minus 5 H's leaves minus 4 H's in the counter. You're probably starting to see the pattern here. You can update with arguments. That's 5 more S's and 5 more P's. As a counter is just a special type of dictionary, you can access a key with a subscript, which means you can loop over your counter. Likewise, counters have a keys method so that you can get at the keys in your counter. And a values method. And an items method. all your inherited dictionary goodness. One behavior of counters that's a little different than dictionaries is when you ask for a key that isn't there. Instead of getting a key error, you get the count. There are 0 A's in Mississippi. Well, Mississippi plus a bunch of other things I did, but there's no A's there. Note that this is case sensitive. Nothing I've typed has a capital letter in it, so asking for one is going to return 0. Another service the counter offers is information on how common the elements in the container are. Consider a counter tracking how many pieces of fruit got sold. The most common method returns a list of tuples. The tuples are the key value pairs in the counter, and the list is in order of frequency. Apples are most common, tomatoes the least. You can pass an argument to most common to limit how many items come back. This is just the most popular type of fruit. And that is the two most popular. Passing in none is the same as no argument. You get back the whole list. Passing in a number bigger than the number of items in the container returns the whole list as well. What about the least common items? Well, there's no method for that, but you can get at it with a bit of work. I'll start by capturing the most common. Remember that this returns a list. And then I call the reversed method on that list. Voila, you've got it all backwards, as intended. There's more than one way to. Oh, wait, I made a promise. Anyhow, you can also call the built in function reversed. This gives you a list reverse iterator, which you can put in a for loop or do whatever else you normally do with an iterator. I'm just going to stick it in the list so you can see the results. One last way to accomplish the same thing. This is slightly harder to read, but a fairly common shortcut. It's called the negative slice. This is a trick that works with the slicing operator to create a reversed list in place. See the description below for an article with more details on this. Now you've seen how to use the class, next up I'll show you some practical applications. In the previous lesson, I introduced you to the counter class. In this lesson, I'll show you a few practical uses of this class. Have you ever wondered how frequently a letter occurs in a block of text? Well, wonder no more. In this first practical application, I'll show you how to use the counter class to count the letters in a file. The file I'll demonstrate with is a text file containing Tim Peters' The Zen of Python. This function finds the frequency of letters in a text file. Line 5 creates a counter for tracking the letters. Line 6 opens the file using the file name argument for the function. Lines 7 through 11 is what count the actual letters. The counting is done by iterating through the lines of the file. This is done by the for loop on line 7. For each line, a list comprehension is created. Let's work through that comprehension a bit at a time. The first thing here is what is being output into the list. In this case, it is the value contained in the variable called char. The for block inside of the comprehension tells you what is going to be inside of char. It's going to iterate over the results of line.lower. Line is a string containing the line from the text file, and lower is a function that returns an all lowercase version of the string. This for block has an additional complexity. It has an inline condition. The value of char is only going to be included in the comprehension if the result of char.isAlpha is true. Putting that all together, the list will contain all the letters in a line after they've been transformed to lowercase and only if they're an alphabetic character. This way, punctuation and numbers won't be included in the comprehension. Finally, line 11 is where the counting happens. The letter counter object is updated. A new instance of a counter based on the list comprehension is passed in to update our letter counter. Remember that a call to update will add to the existing values. The new counter counts the frequency of letters in line letters, and the call to update will add the result to the current set of letter frequencies in letter counter, the totals. Line 13 returns the end result. Let's play with this. First off, I'll import it. Then I'll call the function with a text file. And here's the result. Not surprisingly, to any Scrabble players out there, the letter E is the most common occurrence, and not a single 10-point cue in the whole thing. In case you wanted only the 5 most popular, you can call most common, passing in an argument of 5. A histogram is a bar chart that shows the frequency of data. The counter class is all about frequency, so let's build a chart printing function. If you want to build a simple ASCII bar chart, you're going to need to evaluate the frequency of things to be graphed. Of course, the Python counter can help with this nicely. The key part of the function here is line 5, where a counter is created based on the data passed in. The most common method is called directly and stored. Remember that this returns a list of tuples ordered by frequency. The rest of the code is presentation. Line 6 is a dictionary comprehension. This dictionary will contain key value pairs mapping items to be graphed with the number of symbols in the graph, the ASCII bar in the bar chart. The symbol times frequency part creates a new string, which is the graph symbol, defaulting to the hash sign, repeated frequency times. Multiplication of a string in Python gives you repetition. Note that the order of the items in the dictionary will be the order of the frequency of things being counted. As of Python 3.7, dictionaries are ordered dics by default. They were implemented that way in CPython earlier than that, but as of Python 3.7, it is part of the language spec. If you're running something other than CPython, or a version before 3.5, you would need to implement this with an ordered dict class instead. You should also probably look into upgrading if you can. 3.6 has gone end of life. Line 7 finds the longest label in the graph so that all the labels can be padded to this length. Lines 8 through 10 loop through the chart dictionary, printing a padded version of the label and the resulting bar graph. Let's see this in practice. I've got it imported. Because our function bases the frequency calculations on counter, the data argument can be anything that counter can take. Let's graph some fruit. Now, passing the sales counter into the graph function and changing the graphing symbol for giggles. And once again, a nice little ASCII histogram. For a little homework, see if you can add the ability to scale the graph. Add a max width argument to the function and scale the bars so that they're never longer than that maximum. Should just be a few lines of code. Next up, some more practical applications. In the previous lesson, I showed you how to count letter frequency in a file and how to build an ASCII histogram. In this lesson, I'll continue showing you some more practical applications of the counter class. The mode of a sequence is the value that appears most frequently. Consider the sequence 1, 2, 2, 3. The mode is 2. That is the value that appears most often. Let's write some code to calculate the mode. Dr. Seuss, eat your heart out. The function in the top window here implements a mode calculation. Line 5 shouldn't be a surprise. It creates a counter based on the data passed in. Line 6 gets the count of the most frequent item. Remember that most common returns a list of tuples, so this throws away the most frequent item's name using the underscore convention and stores just the corresponding frequency value in top count. Lines 9 through 11 then loop through the data, finding all the items whose frequency match top count. This will ensure that if there are multiple items that share the top spot, they'll end up in the results list. Let's try this out. Importing it. Now some data. The number 2 shows up 3 times in this data, so it's the mode. How about adding a 3 to have multiple modes? And there you go. Let's try it with something other than a list of numbers. And like previous examples, because the frequency calculation is done through a counter object, anything that counter takes, mode can compute. The mode here is both the apples and the oranges. They're not perfect, but file extensions are a good hint as to what kind of data can be found in a file. The next practical application counts the frequency of different file types in a directory. Let me surprise you by starting out by importing our dear friend counter. And now the path object from pathlib. If you haven't used this module before, it is a more modern version of the os.path library. It does all the same things, but it's a bit easier to use and far easier to read. One of the powers of pathlib is the ability to compose path objects together using the slash operator. Normally, I'm not a big fan of operator overloading. I've seen too much code where it isn't clear what the overloaded operator is supposed to do, but here, paths use slash as separators, and it's easy to ignore the fact that this is actually overriding division of all things. I'm on a Mac, which is a Unix based operating system. If you're on Windows and coding along, you'll have to modify this path to give you something that makes sense in your environment. For me, this joins my home directory path with the downloads directory underneath it. Note that the path object doesn't verify that the path exists until you do something with it. So if you point this somewhere else and make a mistake, your error won't be seen here. Okay, so downloads variable points to a path object, storing a reference to my downloads directory. Let's do something with it. The iterator method on a path object returns an iterator of all the files and directories underneath the path. If the path this path object pointed to wasn't valid, this is where it would fall over. Here, I've built a list comprehension that is listing through all of the entries. Those are the files and directories. For each entry found, it checks if it is a file. If it is, it will be used in the comprehension. This way, child directories don't end up in the list. Instead of storing the entry itself, I'm using another feature of the path object, the .suffix property. This is the extension part of the file name. So to recap, extensions ends up being a list that contains the extensions of each of the file names found in any directory below the downloads path. And to get the frequency info, just create a counter based on that extensions list. For my downloads directory, I have 46 PDF files, 19 PNG files, and loads more. Of course, you can use most common to get at the most frequent items. Quick thing to note, if you look more closely at the counter, you'll see that it isn't case sensitive. There is one PDF doc in here that's all caps that isn't included in those 46. You could fix this by changing the list comprehension to call lower on the suffix. A natural use of a Python counter is a shopping cart. The keys are the items being put in the cart, and the values are the number of the items being purchased. Let's try this out in the REPL. First off, I'll create a dictionary with some prices. See the comment? The reason I'm saying not to do this is because you should never use a float to store money. Floats are not precise and can get you into trouble. If you're coding with money, you should use the decimal class instead. If you want to see what I mean about precision problems, open up a REPL and add zero point 0.1 to zero point 0.2. You might be surprised at the result. Anyhow, caveat being emptored, I've created a counter with the things I'm buying: one copy of the course, three copies of a book, and some wallpaper. I'm assuming it's digital wallpaper, otherwise, this is a bit of a weird store. Let's look at some info about what's in our cart. Using the items method, I can iterate over the counter object. Then I can look up the price for the product, and then calculate the subtotal for the product by multiplying the price by the number of items in the cart. And that long F string prints it all out. The 7.2 Fs you see inside of the F string are format specifiers indicating that the price and subtotals should be 7 characters wide with 2 decimal places shown. And there you have it, the receipt for your cart. For a little homework, add the lines you'd need to print out a total as well. Next up, I'll show you how to use the counter class as a multi-set implementation. In the previous two lessons, I showed some practical applications of the counter class. In this lesson, I'll go a little bit mathy and show you how counters can be a special type of set, the multi-set. A set is a collection of things where each item inside of it is unique. The concept is common enough that Python has included this as a built-in data type. A multi-set is a set without the uniqueness constraint. They're often implemented in a way where you can know how many of each item there is inside. Does this sound familiar? Yep, you can use the counter class as a multiset. Before getting into the details of multisets, I need to introduce you to one more method on the counter object. So far, nothing you haven't seen before. Here's the new part. The elements method returns an iterator of all the items in the counter. Let me put it in a list so you can see the results. This allows you to reconstruct the contents of the original data, albeit in a different order. With that extra bit of info, I can now talk about multisets. A set in math is a collection of things with unique members. Python has a built in data type for handling sets. Here, I've just created one. Note how the multiple ones and fours end up having just a single instance in the set. Now, let's try that with our favorite state. And the same idea, but this time the members are letters. There are cases in math where you want sets without the unique member restriction. Enter Python's counter. You can use the counter object as a multiset. One place where you might want to use a multiset is when dealing with the prime factors of a number. Let me multiply some primes together. Or, thinking of that another way, that's three twos, four fives, and a 17 multiplied together. Putting these factors together in a counter gives a multiset of the prime factors of 85,000. Having that in place, you can determine the resulting number using the elements method. First, let me create a variable to store the result. Next, I'm going to loop over the elements. Remember, this will return each item in the multiset, so three twos, four fives, and a 17. Multiply that and store it into the product. And with that done, you've got a product variable containing the results. If you're using Python 3.8 or greater, you can do this in even less code by using the prod function in the math library. And that gets you to the same place. If you've ever done anything with sets in Python, you'll know that you can perform operations on them, combining them in interesting ways. Counter provides this same functionality to enable you to use it as a multiset. Consider the case of knowing the inventory and then having someone shop. That's my inventory counter and my shopping cart counter. The subtract method on counter updates the value in the counter, subtracting the corresponding amounts from the argument's multiset. The two apples and five oranges that were purchased in the cart have been subtracted from the inventory. Like the other methods on counter, you can use arguments to subtract. Five less oranges. It also supports the dictionary style notation. Counters also support math operations. Consider two counters, each storing the sales for a given day. The total sales for the 2 days can be found by adding the counters. Note that the subtract method that I was showing you just before updates the counter object in place. Addition creates a new counter, combining the data stored in day one and day two together into a third object. Difference is also supported. The sales increment would be how much better you did on day two than day one. Couple things to notice here. Like addition, this is creating a new object. Don't confuse the subtract method with the minus operator. They both do subtraction, but have different effects. The second thing to notice is how difference handles negative values. It ignores them. Day one has 9 oranges, day two has 8. The difference is a negative number, so it isn't included at all. This may or may not be the behavior you want, so be careful. You can combine multisets through both intersection and union operations. The intersection of two counters is the minimum values of the items in the two sets. The AND operator is used for intersection. Union is done through the OR operator. Unions combine the maximum values of the items in the two sets. There are two more operators that I want to talk about that are a little bit weird. They're both unary operators, which means they operate on a single object. Consider an inventory with some negative values. I always seem to end up owing my neighbors tomatoes. Applying the unary plus to the set, and you get a new counter with only the positive values from the inventory. The tomatoes are gone. Doing the same thing with the unary minus, and you get a new counter with only the negative values. but note that you're getting a positive count of them. With a little clever coding, you could combine the idea of the unary plus and the unary minus and build your own subtraction that handled negative numbers without removing them. I'll leave that as an exercise for you. That's it for your introduction to the counter class. Next up, I'll summarize the course. In the previous lesson, I showed you how to use the counter class as a multiset. In this lesson, I'll summarize the course. In this course, I showed you all about counting problems and how to use Python's counter class to help you solve those kinds of problems. Remember that you can initialize the counter with sequences, dictionaries, and arguments, as well as other counter classes. Once you've initialized the counter, you can get the most frequent items in the class by calling the most common method. You can also get the contents using keys, values, items, and elements. In this course, I covered several different practical applications of the counter class, including counting letter frequency, building histograms, determining the statistical mode, counting file types, and building shopping carts. And finally, I went a little math geek and described multisets and their operations and how you can use a counter to implement them. That's all I have on counters. Thanks for your attention. I hope you enjoyed the course. Pause for 1 Mississippi, 2 Mississippi, 3 Mississippi, and fade to black.